The carbon dioxide greenhouse effect. In the 19th century, scientists realized that gases in the atmosphere cause a greenhouse effect which affects the planet's temperature. These scientists were interested chiefly in the possibility that a lower level of carbon dioxide gas might explain the ice ages of the distant past. At the turn of the century, Savante Arrhenius calculated that emissions from human industry might someday bring a global warming. Other scientists dismissed his idea as faulty. In 1938, G.S. Callender argued that the level of carbon dioxide was climbing and raising global temperature, but most scientists found his arguments implausible. It was almost by chance that a few researchers in the 1950s discovered that global warming truly was possible. In the early 1960s, C.D. Keeling measured the level of carbon dioxide in the atmosphere. It was rising fast. Researchers began to take an interest, struggling to understand how the level of carbon dioxide had changed in the past, and how the level was influenced by chemical and biological forces. They found that the gas plays a crucial role in climate change, so that the rising level could gravely affect our future. This essay covers only developments relating directly to carbon dioxide, with a separate essay for other greenhouse gases. Theories are discussed in the essay on simple models of climate. Like many Victorian natural philosophers, John Tyndall was fascinated by a great variety of questions. While he was preparing an important treatise on heat as a mode of motion, he took time to consider geology. Tyndall had hands-on knowledge of the subject, for he was an ardent alpinist. In 1861 he made the first ascent of the Weisshorn. Familiar with glaciers, he had been convinced by the evidence hotly debated among scientists of his day that tens of thousands of years ago, colossal layers of ice had covered all of northern Europe. How could climate possibly change so radically? One possible answer was a change in the composition of the Earth's atmosphere. Beginning with work by Joseph Fourier in the 1820s, scientists had understood that gases in the atmosphere might trap the heat received from the sun. As Fourier put it, energy in the form of visible light from the sun easily penetrates the atmosphere to reach the surface and heat it up, but heat cannot so easily escape back into space. For the air absorbs invisible heat rays, infrared radiation, rising from the surface. The warmed air radiates some of the energy back down to the surface, helping it stay warm. This was the effect that would later be called, by an inaccurate analogy, the greenhouse effect. The equations and data available to 19th-century scientists were far too poor to allow an accurate calculation. Yet the physics was straightforward enough to show that a bare, airless rock at the Earth's distance from the Sun should be far colder than the Earth actually is. Tyndall set out to find whether there was in fact any gas in the atmosphere that could trap heat rays. In 1859, his careful laboratory work identified several gases that did just that. The most important was simple water vapor, H2O. Also effective was carbon dioxide, CO2, although in the atmosphere the gas is only a few parts in 10,000. Just as a sheet of paper will block more light than an entire pool of clear water, so the trace of CO2 altered the balance of heat radiation through the entire atmosphere. For a more complete explanation of how the greenhouse effect works, follow the link at right to the essay on simple models of climate. 1. The next major scientist to consider the Earth's temperature was another man with broad interests, Savante Arrhenius in Stockholm. He too was attracted by the great riddle of the prehistoric ice ages, and he saw CO2 as the key. Why focus on that rare gas rather than water vapor, which was far more abundant? Because the level of water vapor in the atmosphere fluctuated daily, whereas the level of CO2 was set over a geological timescale by emissions from volcanoes. If the emissions changed, the alteration in the CO2 greenhouse effect would only slightly change the global temperature, but that would almost instantly change the average amount of water vapor in the air, which would bring further change through its own greenhouse effect. Thus the level of CO2 acted as a regulator of water vapor, and ultimately determined the planet's long-term equilibrium temperature. Again, for fuller discussion follow the link at right. Savante Arrhenius. In 1896 Arrhenius completed a laborious numerical computation which suggested that cutting the amount of CO2 in the atmosphere by half could lower the temperature in Europe some 4 to 5 degrees Celsius, roughly 7 to 9 degrees Fahrenheit, that is, to an ice age level. But this idea could only answer the riddle of the ice ages if such large changes in atmospheric composition really were possible. For that question Arrhenius turned to a colleague, Arvid Hogbaum. It happened that Hogbaum had compiled estimates for how carbon dioxide cycles through natural geochemical processes, including emission from volcanoes, uptake by the oceans, and so forth. Along the way he had come up with a strange, almost incredible new idea. Hogbaum. It had occurred to Hogbaum to calculate the amounts of CO2 emitted by factories and other industrial sources. Surprisingly, he found that human activities were adding CO2 to the atmosphere at a rate roughly comparable to the natural geochemical processes that emitted or absorbed the gas. As another scientist would put it a decade later, we were evaporating our coal mines into the air. The added gas was not much compared with the volume of CO2 already in the atmosphere. The CO2 released from the burning of coal in the year 1896 would raise the level by scarcely a thousandth part. But the additions might matter if they continued long enough, too. By recent calculations, the total amount of carbon laid up in coal and other fossil deposits that humanity can readily get at and burn is some 10 times greater than the total amount in the atmosphere. So the next CO2 change might not be a cooling decrease, but an increase. Arrhenius made a calculation for doubling the CO2 in the atmosphere, and estimated it would raise the Earth's temperature some 5 to 6 degrees Celsius, averaged over all zones of latitude. 3. Arrhenius did not see that as a problem. He figured that if industry continued to burn fuel at the current, 1896, rate, it would take perhaps 3,000 years for the CO2 level to rise so high. Hogbaum doubted it would ever rise that much. One thing holding back the rise was the oceans. According to a simple calculation, seawater would absorb 5/6 ths of any additional gas. That is roughly true over a long run of many thousand years, but Hogbaum and Arrhenius did not realize that if the gas were emitted more rapidly than they expected, the ocean absorption could lag behind. Anyway, temperatures a few degrees higher hardly sounded like a bad idea in chilly Sweden. Another highly respected scientist, Walter Nernst, even fantasized about setting fire to useless coal seams in order to release enough CO2 to deliberately warm the Earth's climate. 4*. Arrhenius brought up the possibility of future warming in an impressive scientific article and a widely read book. By the time the book was published, 1908, the rate of coal burning was already significantly higher than in 1896, and Arrhenius suggested warming might appear in a few centuries rather than millennia. Yet here, as in his first article, the possibility of warming in some distant future was far from his main point. He mentioned it only in passing, during a detailed discussion of what really interested scientists of his time, the cause of the ice ages. Arrhenius had not quite discovered global warming, but only a curious theoretical concept. 5. An American geologist, T.C. Chamberlain, and a few others took an interest in CO2. How, they wondered, is the gas stored and released as it cycles through the Earth's reservoirs of seawater and minerals, and also through living matter like forests? Chamberlain was emphatic that the level of CO2 in the atmosphere did not necessarily stay the same over the long term. But these scientists too were pursuing the ice ages and other, yet more ancient climate changes, gradual shifts over millions of years. Very different climates, like the balmy age of dinosaurs 100 million years ago, puzzled geologists but seemed to have nothing to do with changes on a human time scale. Nobody took much interest in the hypothetical future warming caused by human industry. Skepticism, 1900 to 1940s. Experts could dismiss the hypothesis because they found Arrhenius's calculation implausible on many grounds. In the first place, he had grossly oversimplified the climate system. Among other things, he had failed to consider how cloudiness might change if the Earth got a little warmer and more humid. A still weightier objection came from a simple laboratory measurement. A few years after Arrhenius published his hypothesis, another scientist in Sweden, Knut Ångström, asked an assistant to measure the passage of infrared radiation through a tube filled with carbon dioxide. The assistant, Herr J. Kook, otherwise unrecorded in history, put in rather less of the gas in total than would be found in a column of air reaching to the top of the atmosphere. The assistant reported that the amount of radiation that got through the tube scarcely changed when he cut the quantity of gas back by a third. Apparently it took only a trace of the gas to saturate the absorption, that is, in the bands of the spectrum where CO2 blocked radiation, it did it so thoroughly that more gas could make little difference. 7 Ångström. Still more persuasive was the fact that water vapor, which is far more abundant in the air than carbon dioxide, also intercepts infrared radiation. In the crude spectrographs of the time, the smeared-out bands of the two gases entirely overlapped one another. More CO2 could not affect radiation in bands of the spectrum that water vapor, as well as CO2 itself, were already blocking entirely. 8. These measurements and arguments had fatal flaws. Herr Kook had reported to Ångström that the absorption had not been reduced by more than 0.4% when he lowered the pressure, but a modern calculation shows that the absorption would have decreased about 1%. Like many a researcher, the assistant was overconfident about his degree of precision, 9 *, but even if he had seen the 1% shift, Ångström would have thought this an insignificant perturbation. He failed to understand that the logic of the experiment was altogether false. The greenhouse effect will in fact operate even if the absorption of radiation were totally saturated in the lower atmosphere. The planet's temperature is regulated by the thin upper layers where radiation does escape easily into space. Adding more greenhouse gas there will change the balance. Moreover, even a 1% change in that delicate balance would make a serious difference in the planet's surface temperature. The logic is rather simple once it is grasped, but it takes a new way of looking at the atmosphere not as a single slab, like the gas in Koch's tube, or the glass over a greenhouse, but as a set of interacting layers. The full explanation is in the essay on simple models, use link at right. The subtle difference was scarcely noticed for many decades, if only because hardly anyone thought the greenhouse effect was worth their attention. After Ångström published his conclusions in 1900, the small group of scientists who had taken an interest in the matter concluded that Arrhenius's hypothesis had been proven wrong and turned to other problems. Arrhenius responded with a long paper, criticizing Koch's measurement in scathing terms. He also developed complicated arguments to explain that absorption of radiation in the upper layers was important, water vapor was not important in those very dry layers, and anyway the bands of the spectrum where water vapor was absorbed did not entirely overlap the CO2 absorption bands. Other scientists seem not to have noticed or understood the paper. Theoretical work on the question stagnated for decades, and so did measurement of the level of CO2 in the atmosphere. 10 *. Radiation math.